So this video is going to look at some unique situations that sometimes occur when you're solving linear systems. Here are these three main methods that we have: substitution, graphing, and combination. In this video I'm going to show you both of these two methods, graphing and combination, and what can occur in some of these special situations. So to best understand this, it's really good to start with the graphing. I think you can come at it different ways, but I think seeing it visually can really help see what's going on. So there are two different systems that we'd like to take a look at here in this video. Let's start with this one. So the question would be, is there a solution that works for both equations? Now we know from graphing that solution can be found when the two lines intersect. So wherever that cross point is. Well, can you imagine a situation where lines don't intersect? That's going to be a situation where there isn't a solution at all. So let's take a look at this one. If we were to graph both of these equations, so y equals 2x plus 7, there is my intercept of 7, and I got a positive slope of 2. So I'm going up 2 over 1, but I'm also going down 2, back 1. And then my other equation has the same slope, so think about that, right? If you got the same slope, but a different intercept, so now I'm at negative 7. Let's see, let me label this. So y equals 2x plus 7. This one is at intercept of negative 7, and still has the exact same slope of positive 2. So if you think about this, these two lines are simply not going to intersect, ever. They're parallel. Well, if they're not going to intersect, then how could we, oops, that's minus 7, 2x minus 7, how could we possibly have a point that is true for both equations? You can't. There are points that are true for here and points that are true for this equation, but no points that are true for both equations. So we know that in this case there is no solution. Now, this just graphed this, so we already know there's going to be no solution. We know that already. Now, let's take a look, though, at how it looks if you do the combination method. How does that look like if you weren't to graph it? Let's say you didn't graph. Let's say you'd use the linear combination. So I'm not going to have any variables drop out unless I do some multiplying. So I'm looking for my opposite coefficients. 2 and 2 are the same but not opposite, so I can make 2 into a negative 2. That means that I multiply this whole equation by negative 1. So I'm going to rewrite this. Negative y equals negative 2x. Let me be accurate here. Negative 2x minus 7, and y, I'm just rewriting the second equation, y equals 2x minus 7. If I add these, let's see, negative y plus, oh, that drops out. So negative y plus y is 0. Negative 2x plus 2x, that's 0. And negative 7, let's be careful here. Let's think. Negative 7 plus negative 7 is negative 14. Okay, now remember, I'm always paying attention to details here. I've got to work slowly and accurately to make this work. So what this is saying is 0 equals negative 14. And you're thinking, what? Yeah, that can't be true. That is never true. There's no situation where 0 is actually equal to negative 14. So there's no solution. There's no variables at work. No solution. So here's how you're coming to the same conclusion, but you've done it two different ways. Once you graphed it and seeing parallel lines, and the other time that you worked it through with the combination method, I saw something funky happening. All right, so that's one unique situation where you have no solution because of parallel lines. But let's consider another possible situation, and then we'll be done with this particular video. What if the two lines were on top of each other? They're essentially the same line. They were equivalent equations. These don't look equivalent, but are they? Well, if you multiply the top one by 2, you'd see that they actually are the same. Let's say you didn't notice that. Let's just say that you know, they didn't pop out at you at first. What would it look like if you graphed it or if you did the elimination method? Well, let's do both. So if we graph that, I think it makes more sense to have it in slope-intercept form. So y equals, I'm going to subtract the 2x from both sides. Y equals negative 2x plus 10. And here, there's going to be a couple steps. So let me do those steps and then write the equation. I'm going to subtract the 4x. So I've got 2y equal to negative 4x plus 20. Now I want the y by itself, so I have slope-intercept form. So I'm going to divide by 2, and I can divide the entire side by 2. The left side is y. Right side is negative 4 divided by 2 is 2, so negative 2x. And 20 divided by 2 is 10. So there it is, 10. Y equals negative 2x plus 10. Let me write that here. Y equals negative 2x plus 10. And voila, what do you notice? Same equation. So if I were to graph that, it's be the same equation. So I'll just do this very quickly. Intercept of 10, slope of negative 2, and I'm not even using my straight edge. I'm just doing it for efficiency's sake. You see there's the line. And then if I graph the other one, it's the exact same line right on top of it. So if I have the exact same line on top of the other line, then how many times do the two lines touch? All the time, right? For absolutely every point. So there are an infinite number of solutions. Any point at which these two lines touch, that is a solution. Now, what's rather interesting is that doesn't mean that any number works. It just means that there are an infinite number that work. So let your mind wrap around that one for a second. Take, for example, this point. I'm just picking it because it's a point on what is really two lines, right? And they're on top of each other. That point is 2, 6. Now I could have chosen any other line or point, right? I could have chosen this one, 5, 0. Doesn't matter. Either one of those and any of the many, in fact, infinite number of other combinations of points or ordered pairs would work. I know that because if I take my original equation, 2x plus y equals 10, and put in 2, 6, I think this will work. So 2 times 2 plus 6 equals 10. 4 plus 6 is 10. Yes. 5, 0 should work too. 2 times 5 plus 0 equals 10. 10 plus 0 is 10. Yeah, I mean, they both work, whether it's 2 and 6 or 5 and 0. And it would work for the other equation because it's the same equation. However, let's say I pick something over here. Well, 7, 6 wouldn't work, right? You can't just pick any numbers. So the crazy thing, if you let your mind get around this one, this is one of those things in math that I find fascinating. There are an infinite, because this line goes on forever, an infinite number of solutions for this system. However, if you look at numbers that are not on the line, there's also an infinite number of solutions that don't work. And if you want to start thinking crazy or so, there's actually levels of infinity. Yes, there's an infinite number here, but there's an even more infinite number of solutions that do not work. So there you go. Chew on that one. All right. Now, let's say that you had actually used the elimination method. What would it look like? Well, you would have tried to get opposite coefficients. So you probably would have, say, multiplied this first one by negative 2. So being careful, that's negative 2 times 2x is negative 4x. Negative 2 times y is negative 2y. Negative 2 times 10 is negative 20. Leave the second equation alone. And watch what happens. I add that up, I get 0. I add that up, I get 0. I add that up, I get 0. Well, when is 0 equal to 0? Always, right? 0 is always equal to 0. So that means that there are an infinite number of solutions to this system. So I hope that was helpful, and thanks so much for watching.